All right. Here we go. Okay, more chain rule stuff. I want to give you. So we did last week. We did the main version of chain rule, right? You can trade scores here in a little bit. Okay, so how about this? So we did this one, right? We did the if we've got a composition of functions, we know how to differentiate a composition by differentiating from the outside, peeling the layers off, and differentiating to the middle, right? As many layers as there are in the composition, that corresponds to the number of links in our chain, right? The links of the chain. And we looked at some pretty tough problems, honestly, doing it that way. Okay, the other form of the chain rule is this way. Okay, I don't know what you even call this, like the Leibniz version or something. But we can write this slightly differently, and sometimes this is useful. So dy dx is equal to dy du times du dx. Okay, and that we've been doing that all along, but we haven't thought of it in this way. This is kind of useful, and notice what happens here. When you write the product of these derivatives, it's literally like you're canceling a factor there, right? The du on the top and the du on the bottom just cancel like factors do when they're on the top and the bottom of a fraction. Okay, when is this useful? Well, here's an example. So I actually put a picture of an analog clock face on there because you guys never use analog clocks anymore, right? But what if we wanted to find ds dh, where we're defining s as the angular position of the second hand? So that's going to, it's going to sweep around once per minute, right? M is the angular position of the minute hand. That sweeps around once per hour. And then the angular position of the hour hand is h, which sweeps around once every how many hours? 12 hours. Okay. So if I want to find ds dh, what is that? First of all, what's that mean? Like, how would we say that is a rate? No, you're on the right track. It's the rate of change of the angular position of the second hand. What's that mean? Like, so angular position just means, it's doing this. It's going around in circles, right? So the angular position would be starts off here, and then there's an angular position a little bit later, and there's an angular position. So the rate of change of the angular position of the second hand relative to, or with respect to, the angular position of the hour hand. In other words, you're looking at, this is what Aubrey was, she was like one word away from finishing this. How many times does it take the second hand to go around for every time the hour hand goes around, right? That's how we could think about it. If we measured angular position in rotations, right? The rate of change of rotation of the second hand with respect to the hour hand, okay? That's a tough one to just answer directly. But if we use, because the hour hand moves very slowly, the second hand moves relatively quickly, but there is another hand on that clock, right? That might make it easier if we use kind of a middleman here, right? What if we broke this up and we considered two different things? What if we considered, for example, ds dm? What is the rate of change of the second hand with respect to the minute hand? In other words, how many times does the second hand have to go around for the minute hand to go around once? What is it? 60, right? Doesn't that make sense? The second hand is moving, in other words, the second hand is moving 60 times faster than the minute hand, right? The minute hand goes around once every hour. The second hand goes around once every minute. But really all we're asking about now is if there are 60 minutes in one revolution for the minute hand, then there must be the second hand must have to go around 60 times for that minute hand to make one lap, right? Does that make sense, everybody? Okay, so that's 60. Okay, what is dm dh? what's the rate of change of the minute hand with respect to the hour hand? In other words, how many revolutions does the minute hand have to make for the hour hand have to make one complete revolution? 12 is right. Doesn't that make sense? Because there are 12 hours, the hour hand has to go through 12 hours to make one revolution. Does that make sense? Minute hand has to go once completely around for every hour, right? So that's 12. Does that make sense? I mean, this would have been a lot easier about 30 years ago before we had digital clocks. People would have gotten this a lot more easily, right? If the minute hand goes around once completely, the hour hand's only gone to there, right? It's only gone 1/12 of the way, okay? Make sense? Okay, so now we can answer our big question, DSDH. Oh my goodness. There we go. Okay, does that make sense? By the chain rule, that has to be true, right? That has to equal. Okay, let's talk about it. Right? By the second version of the chain rule, that has to be true. DSDM times DMDH has to give me DSDH. Okay? Well, what's that give us? That gives us DSDM, you told me was 60 times DMDH, you told me was 12. So there's our answer, 720. Okay? If you think about that one, you have to kind of you just pause and really contemplate that a little bit. That's pretty profound relationship. You know, you can just these piggyback on each other. If the first one is 60, if the second hand's making 60 revolutions per one revolution of the minute hand, and the minute hand's making 12 revolutions per revolution of the hour hand, it just, if you really think about that, this is the only way it could be. It has to be a product, doesn't it? That's what has to relate those. And so that's a good example of how you could use this version of the chain rule. Okay, did we do anything different? No, not really. It's the same thing. It's the same thing we did up here, but it's just a more convenient way to think about it. I mean, it really isn't. If we're saying y is being replaced by the function f, right? dy du, isn't that really just f prime of u, right? Doesn't that make sense? Well, what did we get when we calculated the derivative with respect to x of f of u? We got f prime of u times du dx. Well, that's just u prime, isn't it? That's what we'd call u prime. So this is the same thing we did previously. It's just a more convenient way for a problem like that clock face problem to use this form. Okay, the other thing you could do with this, and I don't want to confuse you, but you could, rather than write this as a product of dy du times du dx, we could divide by the reciprocal of that, right? So sometimes you could even do this. You could say something like dy dx is the same thing as dy du divided by dx du. The du's still cancel out. Okay, sometimes that's convenient. Okay, but that's no big deal. I mean, that's just writing this as a ratio instead of a product. No big deal. Okay. All right, wanted to show that to you. 98.1% of the time we use the top one though. Okay, that's why we focus on that one. I made that up, but most of the time. I don't know what the statistic is, but it's the vast majority. Okay, what about a problem like this? This is like what the first assignment's about. Just thinking about the chain rule and how it works. So if f and g are differentiable on their domains, h is a composition of the two. H of x is f of g of x. If g of 6 is 2 and g prime of 6 is 9, what else do we need to know to calculate h prime of 6. Okay, what's sometimes helpful here is just to think in general. Don't think about h prime of 6. Think about like maybe h prime of x. Okay, you guys remind me, what is h prime of x going to equal if h of x is a composition of those two things? By the chain rule, what do we get? H of x is f of g of x. How many layers in that composition? 2. So I need 2 links in my chain, right? What's the first link? F prime of hand, right? The derivative of f of hand is, oh, what that was, f prime of hand. What's my hand? It's g of x, right? Okay, times, what's the next link then? If we peel back the f part and we look inside, yeah, just g prime of x, right? Okay. Trying to do f of g of x. So what would we need to know then? Well, what is g of 6? They tell us that, don't they? G of 6 is 2. Yeah, exactly. So this whole thing right here. F prime of 2. They didn't give us that. And so if we don't know what the function is here, do like Well, let's see. I haven't even figured it out. So we're doing part A. Not plus. Not plus. Mm-hmm. 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 Right. Okay. So let's look at part A. reviewed that, didn't I, down here somewhere? Yeah, a to the m over a to the n is a to the m minus n. Well, look, 1/2 minus negative 1/2 is, it's all, you just write it as 1 big